function, right? That is exponential growth. And so I know it's going to look something like this. Agreed? Okay. If I asked you to graph another function, I'm going to call it g of x, and it was the log base 2 function, right? Then it is going to do what? Won't it look like this? Yes? And what is the relationship between these two functions? Is there a relationship between these two? They're inverses of each other. They undo one another. That is, when you learned about logs in college algebra, hopefully that's the way they introduced it, is that if you have an exponential function and you want to undo it, then you come in with the log function of the same base, and these are two inverses. So this could be replaced with f inverse of x. These would undo one another. And the way you could tell if you graph them is if you draw that diagonal line, we call that the identity function, then these are mirror images of one another when you graph them. They're reflections over that identity. All right, let's get down to some properties of logs. Oh, you remember these properties? Not do you remember them, do you remember seeing them? This was called expanding and condensing logarithms in college algebra. We're basically going back to the college algebra chapter on exponential and logs, and we're stirring that whole pot up again here. All right, all these things are coming back to life. So we said that if you had log base a and you had two things inside being multiplied, you could split that into addition. If you had division inside of a single log, you could split that into two logs with subtraction. Yes? Okay, and then this was the almighty powerful property that if you had log base a of something to a power, that the power could come out front. That was an awesome property of logs right there. All right. So this was the natural exponential, e to the x. And then, what is the function that undoes that function? Well, log base e, right? Well, log base e has a very special name. It's called the natural log function. And we actually don't write it this way, we write it that way, natural log. Okay, so let me share a little history with you. I hate this notation, personally. I wish that, maybe it's because I teach it. I wish that we always used this notation for all logs. I wish that we always did log, then just wrote what the base was and put x. I don't like this, and there's another one out there, this one. Log x and natural log x. These two right here don't show you what the bases are, right? So you have to remember that this really means log base e, and you have to remember that this really means log base 10. Now here's the historical reason why. The natural log comes up so much in the real world, okay, in terms of science. The natural log function is used so many times that back when people were writing these very long, books or papers, you have a paper that, maybe a 500-page paper that you're going to present to, in some research or something, and you have to use the natural log function maybe, 2,000 times within your paper. Well, back when they were using typewriters, if you ever needed to subscript, right? No one's ever used typewriter? Okay, so you type, mechanical thing hits the paper, ink goes onto the page, but when you want to subscript, you would have to stop and rotate the drum a little half turn, and then type your E, and then rotate it back, and then continue to type. And even if you use a word processor now, like Word or something, subscripting is not just, you just don't continuously go, you don't just type away. So to make it easier on everybody, we just said, don't do this, just do that, and we're all good. We understand what you mean. And so that way you could type without stopping. Make sense? The problem with it is that students have no freaking idea what the base of this log is. It's lost somewhere, the students forget about it. Or they think that this is somehow different. You have log base 2 of x, log base 7 of x, log base a half x. Well, log base ex. right? That's the base, but we don't do that. We do natural log, and then, you see what I mean? You forget that there's an e there. And okay, but this is the way we do it. I'm not going to change it today, right? So there it is, natural log. It is the base e log function. It's the inverse of the natural exponential function. And here's the property of it. If you take natural log, and inside of it you put the other function, it's going to spit out x. That was that loop I just showed you, right? If it goes through one and then back through the other, it's got to go back. So natural log and e kill each other off and the x just falls out. Here you can do it this way also. If you take e and raise it to the natural log of x, they kill each other off and you just get the x. That's the property of the inverses. We also have these properties. E to the 0 is 1. I hope you know that e to the 0 is 1. Natural log of 1 is 0. Why is natural log of 1 0? Why is natural log of 1 0? Yeah, so look, let's just do this picture real quick. If I take 0 and I send it through the e to the x function, e to the 0 is what? 1. Okay, so the inverse function has to take it back to 0, right? What is the inverse of the e function? Natural log, right? So natural log, when you plug 1 into natural log, where must it go?
0.
Back to 0, okay? So natural log of 1 is 0 simply because e to the 0 is 1. And then what's natural log of e? It's just 1. And the way to see this is e is really e to the first power. So what you're doing is you're plugging in 1, right? So you're plugging in 1. It goes through, comes out something, and then where does it go back to? 1. So 1 goes into e, and then natural log sends it back to where it came from. All right. We're getting close. The last thing is the change of base formula. Most calculators do not have but 2 keys on them when it comes to logs. They have usually the natural log key on your calculator, and then they'll have an LOG key. And remember, natural log, the base is e. This is base 10. Why base 10? Why do they have a base 10 key there? Because our number system is base 10. So it kind of makes sense to use to have that there. But it doesn't matter. All you ever need on your calculator is 1 key, just the natural log key, and it's because of this formula right here. It says if you have any log of any base of any value that you want to evaluate. So let's say I want to do log base 7 of 3. Let's say I wanted to do that. I might figure out what that is. Then all I'd have to do is on my calculator type in natural log of 3 over natural log of 7, and that would be the answer. You could also use, yes, the formula also works that you could do log 3 over log 7. You could actually do log base anything, 7, 3 over log base, oh no, let's not do 7, you could do 4. It doesn't matter what log you use. But to make it simple, I'm just going to say natural log. Okay, that's a recap of exponential and log functions from college algebra. In a nutshell, right? Now, derivatives. Because we don't care about all those things. We care about how this ties into calculus. I don't think I want to just give you that right now. Yeah, I don't want to give you that yet. I want to see if we can come up with it. Okay, so here's where I'm going to start. I have to give you something. At this point, well, yeah, maybe not. We can try this. Let's go for it. What is y prime if y equals e to the x? What is the derivative? What is the derivative of e to the x? That's what I'm asking, right? Well, In order for us to figure this out, we have to go back to the limit definition of the derivative to see if we can figure it out or not. So do you remember the limit definition? It's the limit as h goes to 0, f of x plus h minus f of x all over h. Remember that? Okay, so our function here is e to the x, isn't it? That's our function. So what would this limit be? Limit h goes to 0. What do we get if we plug x plus h into that function? E to the x plus h minus what happens when we plug in x? E to the x all over h, right? That's it right there. Okay. How about this? Can I do this? Limit h goes to 0. Is this the same as e to the x times e to the h minus e to the x over h? Yes? I just used properties of exponents, didn't I? This is really this. Now, what do both of these have in common? They both have e to the x, right? And I'm going to pull that out of the limit. So here's where I am. Limit h goes to 0. I pull an e to the x out completely. What am I left with when I pull an e to the x out of the top? E to the h minus 1 over the h that's here. Do y'all see how I pulled that e to the x out of the top and then completely out in front? Now, let's let h go to 0 and see what happens real quick. What would e to the 0 be? 1, right? So this is going to 1. 1 minus 1 is 0. And on the bottom, it's going to 0. We have 0 over 0. That's a problem, isn't it? So we have to see if there's some algebra we can do or something, right? Some trick. And I'm here to tell you there is no algebra and no trick you're going to be able to come up with. Okay? We do not have a way of dealing with this right now. We do not. All right? We will at the end of this chapter. L'Hopital's rule, that thing I was showing you, I said this is very important. Once we have L'Hopital's rule, we'll be able to do that in about 2 seconds. All right? But right now we don't have it. Okay? So you're going to have to take this on faith at this point. What do you think that limit becomes? This right here. What do you think it goes to? Any guess? Goes to 1. This goes to 1, and I'm going to leave question marks. Stay tuned, okay? I will show you why that's 1 later, all right? Stay tuned to that. But it's 1. And if that's 1, if you believe me, then what we get is what? E to the x times 1, which is e to the x. And that means, amazingly, it is its own derivative. All right? The derivative of e to the x is itself. The derivative of e to the x is itself. And I hate giving you things where I can't prove that to you easily. I mean, there are some ways that we could try, but it would take too much time. Okay, you got that? Derivative of e to the x is itself. So I'm going to put this up here, big old stars next to it. Okay? E to the x, its derivative is itself. This is unique. Only function that does this. That says non-trivial. There is another function that does this, all right? It's the function f of x equals 0. What is the derivative of that? 0, right? But this function itself is boring. It's just flat line, that's all it is, right? It's not doing anything interesting. So this is what we call the trivial case, but this is the only non-trivial function that does it. We talked about this earlier. Remember you asked the question? So what that means to us, what this all means is that if I take this function and graph it, e to the x, that if I wanted to know the slope of the tangent line at any point, so let's pick a value x, and I go up here, and I ask you for the slope. I say, hey everyone, what is the slope of that line? What will it be equal to? E to the x. That's what it will be equal to, right? But e to the x is that number right there. Isn't that e to the x? So the slope of this line is actually the height of the point. So if I go here, the slope of the line is not going to be as much, right? Because the point's not as high. The further out I go, the steeper it gets because the higher the point is. Yes? Only one function does that. This is it. All right. Now that's the derivative of e to the x. What about the derivative of a to the x? Where e is the very special function, isn't it? But what about a to the x? So what if you have a to the x? What is its derivative? Well, I'm just going to tell you, all right? I might prove it later, but you can just take this one on faith for now, because you already took that one on faith, right? Okay, the derivative of a to the x is itself, so it's almost that, right? With one more thing, times natural log of a. Now, if you're looking at these two formulas here, and you're looking at which one is more powerful, like which is the big daddy, that's the one right here. Because this one covers all cases. This is a specific case. What? Yeah, this is when a equals e. What, can we see that in the formula? If I were to use that formula here, what would I need to tack on to the end of this? ln of e. But what is ln of e? 1. So this is 1. And therefore, it's just e to the x. Okay? This is a result of this formula. So let's just practice this real quick. I would like for you to take derivative of this versus the derivative of this. So what's the derivative of 4 to the x? 4 to the x times natural log of 4. And please keep in mind, this right here is a constant, isn't it? That's just a number. It's just a number, right? So you have some function, and you've scaled it. So it's like you take this exponential function, its derivative is some scalar multiple of itself. So it like stretches it out vertically or compresses it. But it's not an exact mirror image, or not mirror image, but it's not exact copy right on top of itself. The only one that does that is e to the x. Now, what's the derivative of that one? 4x cubed. Now, I showed you that because here's one of the biggest mistakes I see when it comes to derivatives of exponentials. We'll have something like this happen. Let's say, as an example here, I give you y is equal to 4 to the x times sine x, and I ask for the derivative. What are you going to have to do to take derivative of this? Product rule. Product rule. There's a product right there, right? So you have to do the product rule. So the derivative of 4 to the x first times this plus the derivative of this times this, right? What I see, don't write this down, this is what I see. I see this. So what did this student do?
He did the 4x cubed.
Yep, he did this. No, it was she. I'm sorry. It was she.
He did that. Yeah.
Okay, yeah, we're going to stop right there. Okay. So they're using this rule, right? This is called the power rule. That's what we used when we had our variable raised to a power. But when you have it the other way around, you have a fixed base raised to a variable, right? This is exponential. So what they did is they saw this, they didn't recognize it as an exponential, and they applied the power rule instead, and this is completely incorrect. All right? What it should have been instead is 4 to the x times natural log 4. Now you could put the natural log 4 out in front. It's up to you. Okay, so 4 to the x natural log 4 times sine x plus derivative of sine is cosine times 4 to the x. That's the way it should be done. Understand? Everyone see the product rule there? Yeah. Okay. All right. Let's proceed. We'll do some examples. Probably going to spend more time next class doing examples. But I would like to see if we can't figure out what the derivative of a logarithm is. I know I haven't done a lot of examples today, just that right there. But like I said, next class I will do plenty of examples of derivatives of exponentials and logs. Let's just get the formulas here first. All right, so now let's look at y is equal to log base a of x. And I'm actually going to start out with the general log. Instead of starting with the natural log, the special case, I'm going to start with the general one, see if we can't find its derivative. In this one, I'm not going to ask you to take it on faith. We want to find y prime. So you ready to see how this is done? This is actually pretty cool how I'm going to do this. I know nothing about the derivative of this. No idea, no clue at all. What I do know the derivative of is exponentials, because someone gave that to me, right? And I took it on faith. So what I'm going to do is this. I'm going to take a raised to the y equals a raised to the log base a of x. So what did I just do? It's like I applied an exponential functions to both sides of the equation. Now technically that's not what I did, but you should have done this before, like in college algebra, where like you take e on both sides or you take natural log on both sides. That's basically what I'm doing here. So I did a raised to this side equals a raised to that side. With me? Okay. Now, what does the right side become? What is it? Just x. Because what are you doing? You're taking a, which is an exponential function, and you're raising it to its inverse. And that should kill each other off and just leave you with the x. Right? Y'all okay with that? Now what I'm going to do is I'm going to do this, implicit differentiation. I'm going to take derivative of the left and the right hand sides with respect to x. So I'm going to be doing d dx, if you need a reminder of what I'm doing here. I'm taking d dx on both sides. Let's start with the right side. What's the derivative of x with respect to x? 1. Right? Derivative of x with respect to x is 1. But the derivative of this is going to be a little harder. First of all, what's derivative of a to the y? A to the y? Natural log of a. Okay? So this is a to the y times natural log of a. That's the formula I just gave you, isn't it? But then the chain rule says take the derivative of what's up here, dy dx. And now can you solve for dy dx? Is that okay so far? All I did was took this and divided it on both sides so I get dy dx by itself. Almost there. Almost there. What is a to the y? X, isn't it? So isn't this dy dx equal 1 over x natural log a? I'm replacing a to the y with what it is. It's x, isn't it? And that's the derivative. That's it right there. The derivative of y with respect to x is 1 over x natural log a. So I will write this right here. I'm going to summarize this right here. I'll put some stars next to it because it's important. I'll even box it. If you take log base a of x and you take its derivative, you get 1 over x natural log a. That's your general formula for the derivative of any logarithm. So with that in mind, can anybody tell me what the derivative of natural log of x is?
Which is 1 over x.
1 over x. Now, why is it 1 over x? I need everyone to see this. According to this formula, it's 1 over x times natural log of a. What's the a here? Stupid typewriter, we kind of lose sight of it, right? So it's an e. So this is natural log e. But what's natural log of e? It's 1. So this is just 1 over x. All right, let's just do a quick verbal confirmation of these things. These are all in your formula sheets. What's the derivative of e to the x? E to the x. What's the derivative of natural log of x? 1 over x. I would repeat that to myself enough times that it's in here. Derivative of e to the x is e to the x. Derivative of natural log of x is 1 over x. All right? Get those hardwired as soon as possible. Now, what's the derivative of a to the x? A to the x, natural log a. So you got to tack that other piece on, right? What's the derivative of log base a of x? 1 over x, but then tack on that natural log a down there on the bottom, all right? So the only difference between the general formulas and the natural exponential and logs is that natural log a piece that has to be tacked on. Understand? All right, so I still have time. I'm going to do a couple of good examples here. I don't know if y'all are happy to be here. I'm actually kind of happy to be here today. My spring break was nothing but, I was just doing nothing but manual labor the entire spring break. I got that concrete, poured a 500 square foot concrete patio slab. I did a French drain. I planted 40 red tips.
Who dug the French drain?
I did.
You dug the whole thing?
Yeah, well, it's only about 40 feet long. But I'm going through, it's like caliche. It's like, yeah, it's horrible. Well, caliche's not
You
soft.
are happy to be out of there, I bet.
So I'm like, I've got calluses and stuff. I'm like, man. So I'm actually relieved to be in air conditioning. I love that work though, man. I love being out there working, but it's just, I think today I needed a break. I'd rather work my brain today. All right, let's take a look. Example here. I'm going to let you mess with this one, see if you can figure out what this is. Try and find the derivative of that. E to the x squared. Your hint is that you have to use chain rule. Y is e to the x squared. If it helps, I'll put my eraser up here. Think about what the derivative of e to my eraser is first, and then uncover the eraser and go do the rest. So I'll give you about 10, 15 more seconds, see what you come up with. Okay, what do you got? Someone from that table? No? Any guess?
2x.
The whole derivative? Okay, e to the 2x, close. So think about this. If this was e to the x, the derivative would be e to the x, right? But it's e to this, right? To my fist. So the derivative of e to my fist should be e to my fist. Agreed? Okay, so I'm going to write down e to the x squared. So you have taken the derivative of the e part, haven't you? Yeah. What you have not done is taking derivative of the exponent. You've actually not done the derivative of this yet. So this is chain rule. We're going to say times now the derivative of this, 2x. Does that make sense? Okay. Now you could leave it like this, or you could move the 2x out front. So the different things I see with a problem like that are incorrect, people will do this. That's trying to do too much at one time. It's like you took the derivative of e and the exponent at the same time instead of doing the derivative of the e part first times now the derivative of the exponent. So this is no good. All right, let's try this one. Same thing. Start with the derivative of e to something, times, and then do the rest. All right, what do you got here? Let's see. Back table? Y'all have anything? Anyone? Go ahead. Okay, e raised to the x sine x. So you just basically like copied and pasted that, right? That's exactly what you do when you see e to something. Then, times good. Then you have to say times the derivative of what's here, which was a product rule. And we're going to need to throw that in parentheses because we're going to have an addition symbol in there, and that e to the x sine x will have to distribute. So did you do the product? 1 times sine x, which I'm just going to put sine x, cosine x, x cosine x. Good. Okay. That's it. Now, I want to point something out, that in your formula sheets, okay, they have these versions of the formulas written down, which you might find even more useful than what I put on the board today. This takes into account this chain rule. For example, if we have e to the x squared, right? E to the x squared. Then what you do is you write down e to the x squared, and then you multiply that times the derivative of that x squared. Or e to the x sine x times the derivative of x sine x. And so this formula and this formula are on your formula sheets. You could get used to those if you want. But it's really just the chain. All it is the chain rule here. That's all that's happening. All right, let's go. How about this one? How about y is equal to natural log sine x. You can try and use this formula if you want. If you get that one, I'm going to pass the test out while y'all are doing this. If you get that one, try that one. I'll call your name and then I'll hand these back. Let's see here. Jacob C. Nathan. And Laura. Sophia. I don't even know if the grades are on here, but the grades are online. Hugo. Is it Jason Morgan? Yes. Tara. Tara Knoll. Hold on.
Yeah.
You're Knoll? Tara Gass. Catherine. Benjamin. Nicholas. Emma, and Ryan, Ruben, and Diego. Let's see, Haley. How do you say this? Is it Lourdes? Lourdes? See, Christian, Jason, Manuel. All right. Anybody want to write the answer on the board? Zachary, Mary, Nicholas, Jonathan, Tatiana. There you are. That's it. That's everyone's. Everyone have theirs? Okay, let's go with some answers here. How about that first one? You're going to do 1 over u and then times the derivative of the u. So what do you got? 1 over sine x times cosine x. Hey. That's cotangent x. That's cosine over sine. Okay, how about this one? It's 4 to all that junk, right? We're going to say 4 to all this stuff. Then you say times natural log of 4, then times the derivative of all that stuff up there. 2x plus 4. So it's like you make a carbon copy of it, but then you have to tack in that natural log 4, but then you have to take derivative of what's up here, which goes here. All right, we will do more of this when we come back on Wednesday. Have a good day.